So, here's what I want you to think about. Let's suppose we have a transformation matrix that looks something like this. Let's keep it to, 2, 0, 0, 2. So this is my transformation matrix, okay? Can anybody tell me what is that transformation matrix? How would you describe it verbally?
A stretch scale factor 2 by x and y directions.
Perfect. Where's the center?
Center?
Yes, it's the origin, isn't it? Yeah, it's centered at the origin. So it's a stretch in both the x and the y direction by a scale factor of 2, and you're keeping it stuck at the origin, okay? So what if I wanted to visualize this? So let's suppose I have a coordinate axis like this. I'd love you to draw this out as well, okay? I originally started here, okay? In fact, I'm going to put my coordinates on here now. So I started at 1, okay, 1, 0, okay? And J started up here at 0, 1, okay? J started here at 0, 1, right? Now I'm going to put a few more on here, so 2 and 3, and 2 and 3, okay? And let's suppose I take a square. So you saw me do this on the screen on Wednesday. So let's suppose I take a square that looks something like this, okay? And let's suppose that this square was A, B, C, D. So let's suppose that was A, that was B, that was C, and that was D. So who can tell me what are the coordinates of A? 1, 1. What are the coordinates of B?
2, 1.
Good. 1, 2, I think you mean.
2, yeah.
What are the coordinates of D?
2, 1.
Okay, 2, 1. And what are the coordinates of C?
2,
2, 2. Okay, fantastic. All right, so here's what I want you to do. I want you to enlarge this shape by a scale factor of 2 centered at the origin. In other words, I want you to take each one of these coordinates and I want you to multiply that coordinate matrix by this. So how would we do that? Well, first of all, we'd write ourselves out a coordinate matrix. So this column would correspond to A, this column would correspond to B, this column would correspond to the coordinate C, and this column would correspond to D. Okay, so I'm just going to put each of my coordinates in this matrix here. So A will be 1, 1, B will be 1, 2, C will be 2, 2, and D will be 2, 1. So here's my task for you. All I want you to do is multiply these two matrices together. And that will tell you where the new coordinate of A will end up, new coordinate B will end up, new coordinate C will end up, and the new coordinate of D will end up. So can I give you 30 seconds to multiply those two matrices together for me? All right, so could somebody tell me what we get? So what do we get as here? Can we read across the rows first? So you get 2, 2, 4, 4. What do we get here?
2, 4, 4, 2.
Okay. Now can anybody remember what does each column in this matrix, this new matrix, correspond to?
The first row is the I and the second J. No?
Not quite I and J, because remember this corresponds to the new I and the new J. Okay, so in other words, after you stretch it. Good, so exactly. So you mean the x and y coordinates of each of the corresponding points. Yeah? So this first column here would correspond to the new coordinates of A. The new coordinates of A. So in other words, A will end up at 2, 2. So A was here, it now ends up over here. In fact, I'm going to use that as an A dash to show it's the new coordinate of A. This column here corresponds to the new coordinates of B, because the second column was the coordinates of B in my coordinate matrix. So as B ends up at 2, 4. In fact, let me make this a little bit longer. There we go. Let's fold those up there. Good. I'll make that a little bit longer as well. Okay. Yeah, good. So B ends up at 2, 4. So it ends up at 2, 4. That's new B. All right? This is the new coordinates of C. So C ends up at 4, 4, which is way over here. Okay, so new C. And this is the new coordinates of D, right? So 4, 2 is there. All right, okay, good. So in other words, I get a new shape. I get a new shape. And it looks something like that. Now here's my question. Here's my question. We've enlarged this shape by 2 in each direction. Are you happy with that? Okay. What was the area of my old shape? What was the area of this? Good. Because you're happy each side was just 1 unit in length. So the area must be equal to 1. Now here's my question. What's the area of this new shape? Do we agree? What's the area? It's 4, right? Because each length now is 2. Like, look, we're going from 2 to 4, 2 to 4. Do you see that? Okay. So the area is now equal to 4. So in other words, after I've applied my transformation, I'm stretching it by 2 in each direction, but the area has been enlarged by a scale factor of 4. Now, if only there was a way of working out how much bigger my area is going to be from this transformation matrix. Does anybody know how we do this? Well, you could square it, but if you square it, you get a 4 there, a 0 there, a 0 there, and a 4 there. So you can kind of see 4s going on, but all I'm after is just a single number, not a matrix, a single number. Has anybody looked at this before? Does anybody know? No? So we're looking at this matrix, and the question is, can we extract how many times the new area of the shape is going to be just purely from that matrix? And yes, we can. It's using something called, and it's a fancy name, but don't worry, a determinant. Okay? Because it determines the area of the new shape. It determines how much bigger the area of the new shape is going to be. Okay? So here's how it works. With this example here, we take 2, 0, 0, 2. That's my transformation matrix. And all we do is we multiply these 2 elements together. So in other words, we take 2 and we multiply it by 2. And then we subtract that from the other 2 elements multiplied together. So you see we're multiplying elements along the diagonals. Does anybody recognize doing this before? Yeah? Maybe? No? Okay. So you're happy, all I've done here is I've taken the leading diagonal, in other words the one that goes from top left to bottom right, multiplied those together, I get 2 times 2, and I'm subtracting these 2 elements multiplied together. So 0 times 0, which makes 0. So 2 times 2 makes 4, take away 0, the answer is 4. But I want you to not lose track of what's actually happening here. What this number corresponds to, what the determinant of a matrix corresponds to, it's how many times bigger the new area of my shape is going to be compared to my old area. Okay, now I just used squares for the sake of argument, but are you happy I could have used any original shape I like? Any original shape I like. Okay? This number, the determinant, will tell me how many times bigger the new area is going to be relative to the old shape. So if my old shape had an area of 6, my new shape, after I've applied this transformation matrix to it, will have an area of 24. Okay? If my old shape had an area of 70, my new shape will have an area of 70 times 4, which is 280, right? And it worked out by using this transformation matrix here. So this is, if you like, my area scale factor. Does that make sense? Yeah, does that make sense? So I think now we're in a position to generalize, okay? I did it with a specific example, 2002. That was my specific transformation matrix. What if I just give you some random transformation matrix that has an element here, an element here, an element here, and an element here? Okay, so A, B, C, D. All right. If I want to work out the determinant of this, by the way, to work out the determinant of a matrix, we use absolute value symbols. Okay, absolute value symbols like that. Okay, to work out the determinant of a matrix, I should get rid of that. We simply take the leading diagonal, in other words, A and D, and multiply them together. So A multiplied by D. And then we subtract that from the non-leading diagonal elements multiplied together. So in this case, B and C. Multiply those together. This is how you work out the determinant of a matrix.
But every time starting from from the left side, yeah? From
Yeah,
A.
top left to bottom right, so the leading diagonal, okay? And then these two elements multiply together as well. Yeah, so it's important to get the order right, okay? It's always top left to bottom right. Get that one done first, then we do that one, okay?